In this video, we will continue our look at benzene and related compounds by reviewing spectroscopy. In IR spectroscopy, we will be looking for sp2 hybridized CH bonds, which typically absorb just above 3,000 inverse centimeters. And we will also be looking for the aromatic carbon-carbon bonds. These usually show up as two sharp but not always strong peaks, and they're usually not the same strength, but these show up around 1,500 and 1,600 inverse centimeters. In contrast, if you have an alkene, that carbon-carbon double bond tends to show up around 1650. So that's just another reminder that an aromatic ring is not just several alkenes. There is something different about this. Often, these are the only important signals that we're going to see, but sometimes we are going to get useful information out of the OOP region, so the out-of-plane bending, which is around 600 to 900 inverse centimeters. We don't always have to fully interpret this, but in some cases it may be possible to see distinctive peaks in the OOP region that can be correlated to particular substitution patterns on a benzene ring. And related to the OOP region is the overtone region. This is around 1667 to 2000. So if you have a carbonyl around 1700, well, then that's going to block this and we won't be able to see anything. But if we don't have a carbonyl, there's not a lot of other things that absorb in this region. And so you might be able to see some specific patterns which correspond to specific substitution patterns. Generally, we are not going to have to interpret these with the problems that we cover in lecture, but sometimes it might be useful in lab, for example, to be able to dig out a little more information from your IR spectrum. With proton NMR spectroscopy, we are looking for aromatic hydrogens. So this would be a hydrogen directly connected to an aromatic ring. These are going to absorb around 6 to 8, maybe a little higher, up to 8.5 ppm. And if we have a hydrogen connected to a carbon that's connected to the benzene ring, in other words, a benzylic hydrogen, these tend to absorb around 2 to 3 ppm. So the range for aromatics, this is not just due to electronegativity. This is caused by ring current that occurs when the benzene ring is in an applied magnetic field. Within an applied magnetic field, the benzene will have circulating pi electrons, which generates a ring current, and then the ring current generates an induced magnetic field. So this magnetic field will oppose the applied field inside the ring, but it will add to the applied field outside of the ring. So this is called diamagnetic anisotropy, and this is what's responsible for the unusually high absorption by aromatics. You're not responsible for understanding the details of diamagnetic anisotropy, but you are responsible for recognizing the ranges of aromatic hydrogens. By C13 NMR, our aromatic carbons will absorb typically around 110 to 175 ppm. Now, this overlaps significantly with the alkene region. So if we're looking at a particular signal, it will be difficult to determine whether that one signal is due to an alkene carbon or an aromatic carbon. So sometimes we can get more information based on the number of signals in the region. If we only have 2 signals, then maybe it's just an alkene and not a benzene ring. But if we have 4 or 5 or 6 signals, then maybe we are dealing with an aromatic ring rather than multiple alkenes. Often in C13 NMR, the number of signals can be especially important to consider the symmetry within a molecule, which can help you to determine the substitution pattern around a benzene ring. Here we have IR spectra of orthoxylene, paraxylene, and metaxylene. So xylene is a benzene ring with a methyl group and another methyl group. So the first one is ortho, the second para, and the bottom one is meta. Notice we have above 3000, we have our sp2ch, and below we have our sp3ch, and we have that in all three of these spectra. We also have, this is 1500, so we have a signal at 1500 and 1600. So they're different in energy. They tend to be sharp, but not necessarily the same strength. These correspond to the aromatic carbon-carbon bonds. Here we have our 1500 is a lot stronger, our 1600 is pretty weak, but in this one, our 1500 and 1600 are about the same strength. Once you notice that you have sp2chs, then you should look around 1650 to try to find an alkene carbon-carbon double bond, or the 15 and 1600 to try to find an aromatic ring. Another thing I wanted to point out as we're looking at these three spectra is the OOP region, the out of plane bending. And here we are from about 600 up to about 900. And there's not much here except for this one strong peak. In this case, it's a little over 700. Here we have a single strong peak, which is at 800. And here we have two strong peaks at about 700 and almost 800. So ortho compared to para compared to meta, we're going to see different peaks in the OOP region that can be matched to the different substitution patterns. In addition, if we look up here between about 1666 up to 2000, this is the overtone region. Here it looks like very weak signals. Here we have these two signals, and that is an example of a particular pattern that can be matched to the substitution pattern. And if we look at this one, here we have more significant peaks in the overtone region, which can be used to get more information. Normally, just identifying that we have sp2ch in addition to our sp3ch and identifying the aromatic carbon-carbon bonds at 1500 and 1600, that might be sufficient information to get out of your IR spectrum, because that information will be coupled with other data such as proton and C13 NMR. But I just want you to be aware that it is possible to find additional information as well. So finally, let's take a look at the data for a particular compound and try to figure out what that compound would be. Starting with the IR spectrum, we have sp2chs above 3000 and sp3chs below 3000, and then we have our aromatic carbon-carbon bonds at about 1500 and 1600. If we really wanted to, we could find a resource that lists the patterns of the OOP and the overtone region, and we could get more information. But for now, having sp2ch and sp3ch and having our benzene ring, that gives us plenty of information to work with. Next, if we take a look at the proton NMR spectrum, let's call this signal A, B, C, D, and E. Here we are looking at overlapping signals in the aromatic region. And we have an integration of 5 hydrogens, which tells us that this must be a benzene ring with 1 substituent, and then the 5 hydrogens. Now, this is not a single signal. If we have a monosubstituted benzene, we know that these hydrogens are equivalent to each other, but they are different from these hydrogens, which are equivalent to each other, different from this one. However, these 3 signals in the aromatic region could overlap, and that's what we have here. Signal B is at about 2.5, so that would make sense for a benzylic position. So we have a CH because it integrates to one hydrogen. Looks like we have 6 peaks, so probably 5 neighbors. So maybe we have a methyl group and a CH2 group. C absorbs around 1.6 ppm, so it's a little bit deshielded, but not deshielded enough to be directly next to anything special. So this would be a CH2 group, and it has several neighbors. Next, if we look at signal D, we have 3 hydrogens, so this is probably a CH3 group. It appears as a doublet, so it must have one neighbor. So this CH3 is next to a CH. It appears just above 1 ppm, so it's pretty much a typical CH. And then finally, we have another CH3, and this one is a triplet, which means it has 2 neighbors, so this must be next to a CH2 group. So if we put these pieces together, we have our benzene ring, and this gives us multiple signals, which we are lumping together as A. That must be next to a CH, which is connected to a CH3. The CH is also connected to a CH2, and the CH2 must be connected to a CH3. So this would be signal B. It has 5 neighbors. This would be C, D, and E. A, these are aromatic hydrogens, and we have 5 of them, so we would expect them between 6.5 to 8.5 and to integrate to 5. So that works. B should integrate to 1 hydrogen. It should be split by 5 neighbors, and it should absorb between about 2 to 3 because it is next to the benzene ring. C should integrate to 2 hydrogens, and we have 4 neighbors, so we would expect a pentet, and it's probably just a little bit higher than 1, and that's exactly what we have. D would integrate to 3 hydrogens, and it should be a doublet split by 1 neighbor. That's what we have. And finally, E should integrate to 3 hydrogens. It should be split into a triplet, and it should absorb around 1, and that's what we have. So finally, if we just double check our structure, looking at the C13 NMR, we have signal A, B, C, D, E, F, G, and H. So these carbons are in the aromatic region. So if we have our benzene that is monosubstituted, then we should have 1 aromatic carbon, and then we should have another signal for these 2 aromatic carbons that are equivalent to each other, another signal for these 2, and then another aromatic signal. So 4 signals in the aromatic region that fits with our structure. And then EFGH, these are all sp3 hybridized carbons. So it's probably, this is E, this is probably F, G, and H. So we can use the different information from IR, from proton NMR, and from C13 NMR to determine our structure.